Well, thank you. So yesterday we finished sort of with the finite group actions. So I'm just going to continue with that. So yesterday we discussed the case where we have the symmetric group acting on an n-dimensional vector space by permutations. And actually, for most of what I'm going to say, the characteristic of the field can be arbitrary. So we don't need linearly reductive. And so last time I showed that the invariants for the symmetric group are generated by the elementary symmetric functions. Now, if we have a subgroup, let's say G is a subgroup of Sn, then G also acts by permutation. So this is a permutation representation of the group. And in that case, we have a degree bound for the invariant ring given by Goebel. Around 1995. Namely, so remember this beta, this is a bound for the degree up to which you have to go to find a set of generating invariants. This is less or equal than the maximum of n, and n choose 2. Now, if we're, for example, in characteristic 0, then we have primary invariants and secondary invariants. Then we can just take the invariants for Sn. These elementary symmetric functions form a set of primary invariants. And then the secondary invariants, these are module generators, you get a degree bound of n choose 2. But this bound even holds even if we are an arbitrary characteristic. And basically, Goebel gave an algorithm to find these invariants, or even, there's also an algorithm to express these invariants in terms of generating invariants. And in some sense, the generators you need besides the elementary symmetric functions is you take monomials, and then you sum a monomial over its orbit. And you only take monomials for which the exponents in x1 up to xn, if there's no gap in those exponents. And so the largest degree of such a monomial would be degree 0 plus 1 plus 2 up to n minus 1, which gives you this bound.
Hey, Harm?
Yes?
Is there also a bound on the regularity or not?
Yeah, there's various bounds for... Yeah, there's some bounds on relations, and also, but that also kind of depends on whether we're in a linearly reductive case or not, and so on. So, yeah, there's sort of probably there's sort of many results in that direction as well. Okay. Now, maybe an interesting example is where we take G to be the alternating group. So yesterday there was a question about the case, what if we restrict to the alternating group? So let's take the characteristic of K not equal to 2. And we can define this invariant, which I call delta, which is sort of the discriminant or the square root of the discriminant in a way. Sorry, without the square. So this is not invariant under the group Sn, because Sn acts on this by a sign, but it's invariant under An. And so in this case, the invariant ring is, in fact, you can write it as a module over the invariant ring of Sn. So as a module over the invariant ring of Sn, it's generated by 1 and this invariant delta. In characteristic 2, something similar is true, but this one will also be invariant under the alternating group. They have to take a slightly different delta. Yeah, so in this case, we see that the invariant ring is generated by the elementary symmetric functions and this delta. And so we see in that case, we have equality here, right? Because, yeah, the maximum degree is exactly this maximum of these two numbers. But this is a very special case, right? So these are permutation representations. So what about if you have an arbitrary representation of a finite group? Now there was already a bound by Noether, Emmy Noether, in 1916, which is true in the characteristic 0 case. And this bound was further generalized to the non-modular case, which means the case where the characteristic of K it does not provide the group order, by Fleischmann in 2000, and almost around the same time also by Fogarty, 2001. So this bound says that the invariant ring is always generated by invariance of degree at most the group order. And now it turns out this bound, if we're not in this case where the characteristic doesn't divide, if the characteristic does divide the group order, then this statement actually can be false. So for example, let's take G to be the group generated by a 2-cycle. So this acts on a 2-dimensional vector space again by permutations. And now let's take W, you take 3 copies. Okay, so then in this case, invariant ring, the bound is actually equal to 3, which is more than 2, which is the group order in this case. Oh yeah, and I should have said the characteristic of K, we take it to be equal to 2, right? So you see in this case, the characteristic divides the group order. And in fact, so if you take this coordinate ring, you can think of it as a polynomial ring in, say, x1, x2, y1, y2, z1, z2 for the 3 copies. For example, if you then take this invariant x1, y1, z1 plus x2, y2, z2, so the group acts by switching 1 and 2. So this is invariant, but this invariant you cannot express in smaller degree invariants. So this is an example by Richards. In fact, more generally, we can show that if you take n copies, and this is equal to n. So there's not even a universal bound for even this fixed group. Oh. However, there's still a more recent result by Simons, 2011, gives sort of the following general bound, that even if we are sort of in this non-linearly reductive case, we still have this bound n times g minus 1, where let's say g is not that non-trivial, and n, let's say, at least 2. Then we have this bound. Now, one thing which is also nice about finite groups is that we can actually compute the Hilbert series of the invariant ring without first having to compute the generators of the invariant ring. So you can compute the Hilbert series of the invariant ring a priori. So let me just say a little bit about Hilbert series. Right, so if you have a graded algebra where each K-algebra where each AD has finite dimension, then we can define the Hilbert series, which is a power series in T, which, it's just a generating function of these dimensions of these graded pieces. So that's, I guess, a power series in T. If you have two graded algebras, you can define the tensor product, right? So if you have something of degree D here and something of degree E, then the tensor product will have degree D plus E. And if you define the grading that way, then the Hilbert series of the tensor product is just the product of the Hilbert series. If you have a polynomial ring, and maybe I'll do it sort of in general, where we have a polynomial ring, say P1 up to PR are, say, algebraically independent, and the degree of Pi is, say, Di, so I allow them to have different degrees, then the Hilbert series of this is a product of 1 over 1 minus t to the power di, where I is 1, goes up to d. Okay. So let's now assume we have a representation, so n-dimensional representation of G, where G is finite. Also, I'm going to assume now that the characteristic of K is equal to 0. And some of the statements I'm going to say could actually be generalized to sort of the non-modular case where the characteristic doesn't divide the group order, but then you would have to modify the statement a bit. But in principle, it still works. But I'm just going to assume characteristic 0. So then, so this representation, think of it as a homomorphism from this algebraic group G to GLV. And so then we can look at the identity minus T times rho of G, if G is an element of the group. And we can take the determinant. So that is now a polynomial in T, a polynomial in T of degree n. So then we have the following formula. So this is Molien's formula. So the Hilbert series of the invariant ring is we take this 1 over this determinant of I minus T times rho G. And now we take sort of the average over the group. And so that's the formula for the Hilbert series. So this is a rational function. And so sum of rational functions, so this is going to be a rational function. In fact, whenever you have a finely generated algebra, the Hilbert series is always a rational function, which I believe Hilbert also proved in his, I think, 1890 paper. Because he actually showed that ideals have finite resolutions and things like that. Anyway, so we have this formula. And so this is nice because you can a priori compute the Hilbert series. So let's do an example. So this is really fairly easy to compute, so you can do it by hand. So for example, if you take G is A4, for example, and V is K4, so just the example that we did before, but for n is equal to 4. So G acts by permutations. So then we can look at the group elements. Now there are 12 group elements, but we don't really have to sum 12 things, because if two group elements are conjugate, then this expression will be the same. So we can group them together. And in A4, there are only 3 conjugacy classes. There's the identity, there's a product of two cycles, and there's a 3 cycle, right? And so if you look at the size of the conjugacy class, then there's just one of this, the 3 of these, and the 8 of the 8 3 cycles. And so then if you look at the determinant of I minus t rho g, this is just 1 minus t to the power 4, because it's just 1 minus t times the identity matrix. This is 1 minus t square times square, and this is 1 minus t, 1 minus t cubed. So, so these exponents here, these are exactly the length of all the cycles that appear in the representation, because that's always the case for permutation representation. And so then we get the following formula in this case. It's 1 over 12 times 1 over 1 minus t to the power 4 plus 3 over 1 minus t square plus 8 times 1 minus t cubed. And then, well, you have to do some calculations. You can simplify it. You get something like 1 minus t squared plus t to the power 4 over 1 minus t. So we kind of make the same denominator. And then this is what we get. But I can, if I multiply by numerator and denominator by 1 plus t squared, I can also write it as 1 plus t to the power 6, 1 minus t times 1 minus t squared times 1 minus t cubed, 1 minus t to the power 4. And then this is really 1 plus t to the power 6 times the Hilbert series of the invariant ring for Sn, which is generated by the elementary symmetric functions. And so this 1 and 6, they correspond to these module generators, 1 and delta. So delta in this case has degree 6 for n is equal to 4, right? So in general, right?
That's one half equivalent formula if G is compact, taking an integral.
Yes, one can, yes.
It's true also.
Yeah. And I'll do some examples of that. We can actually say a little bit more about this power series. So in general, again, so you can write it as a Laurent series. And if rho is injective, which we may assume without loss of generality, then A0 is always exactly 1 over the group order. And A1 is, say, K over the group order, where K is the number of, I guess, generalized reflections, I think I have to say. So generalized reflection is some group element that fixes a hyperplane. So this is nice. By the way, if you think about A0, another interpretation is, right, you can take the limit of 1 minus t to the power n times the Hilbert series. Sorry. And then take the limit t goes to 1. So that's another way of obtaining this A0. And if we then use, let's see. Oh, sorry. Sorry, I'm running ahead of, sorry. I first wanted to say something else. Suppose so we're in characteristic 0, so the invariant ring is Cohen-Macaulay, and we have this, we have primary and secondary invariants, right? So we have this, we can write this as PH1 plus PH2 plus up to PHJ, and P is a polynomial ring where these PIs are homogeneous invariants and they are algebraically independent. So these are primary invariants. So then, in that case, the Hilbert series is just sum t to the power ej divided by product 1 minus t to the power di. I is 1 to n, j is 1 to s. Sorry, this is s. Where di is the degree of these primary invariants and ej is the degree of the secondary invariants. So this Hilbert series tells us a lot about the structure of the invariant ring. And for example, if once we have primary invariants, once we know the d's, we can multiply this polynomial with the Hilbert series, and then we can see exactly in which degree the secondary invariance appears. So these are things that one can use in algorithms to find generators, because it helps to know in which degree you have to look. And what I was going to say here, if we take this limit, if you apply it to this formula here, you see using L'Hopital's rule, you see that you get S over the product of the DIs. So this A0 tells you, if you know this A0, then and you have fixed the degrees of the primary invariants, then you know exactly how many secondary invariants you're going to get. So this tells us something about, in some sense, it tells us something about, you know, if you have this quotient, you can think of this as a variety, but it's not, you know, the coordinate ring, projective coordinate ring, is not graded, you know, generated in degree 1. So you can define a degree for such a variety, but it may be a rational number, not necessarily an integer. All right. So that's finite groups. Another example is tori. Right. So a torus is just, you know, product of multiplicative groups. And so we have maybe some representation. And these actions are always diagonalizable. So we can, if you have some z in the torus, let's call it z1 up to zr, then this row of z is of the form, maybe write this z to the power omega 1, z omega 2, etc., z omega n, where z to the power omega I is z1 to the power omega I1, z2 omega I2, and so on. Okay, so this omega, think of that as a vector, omega I1 up to omega IR in z to the power r. So that's the weight of the ith coordinate. So this OV, you can think of that as the polynomial ring in n variables. And then the invariant ring is generated by just monomials. And which monomials are invariant? So x to the power alpha, which is x1 to the power alpha 1, x2 to the power alpha 2, up to xn to the power alpha n, is invariant under the Storrs action if and only if sum of alpha I omega I is equal to 0. So then it becomes sort of more a problem about monoids and finding generators of a monoid. It can sort of be the problem of finding generators of the invariant ring can be formulated in those terms. I think we've also seen in other talks, there's also a nice description of the null cone in this case. By the way, for finite groups, the null cone is sort of trivial, it's always just the origin. But for tori, it could be something interesting. If we have some vector, say v1 up to vn in V, then this lies in the null cone if and only if null, 0, does not lie in the convex hull of all the weights omega I for which vi is not equal to 0. So that's sort of the support of this vector v. If you take the convex hull of that and it doesn't contain 0, then basically there's a one parameter subgroup that sends this v to 0, which means it lies in the null cone. And also there's a nice degree bound for the torus case. So by the way, so what this means is that this null cone is basically...
and you mean omega I is alpha I? Oh, no.
No.
Oh, no, yes,
Yeah.
sorry.
So this null cone is a union of subspaces, of hyperplane, of coordinate subspaces. So it has sort of a nice geometric picture, although it could be union of subspaces of different dimensions, so it could still be combinatorially pretty complicated. Also, the degree bounds are in terms of these weights. So we have the following result by the Gray law that gives a degree bound for the invariant ring. So, by the way, tori are always linearly reductive regardless of the characteristic of the field. Times r factorial times the volume of the convex hull, sorry, I'm running out of space, of omega 1 up to omega n. So you take the convex hull of all the weights, you take the volume, but you multiply it with r factorial, which is sort of some kind of normalization that, like, the smallest possible simplex has volume 1. And then multiply with this constant, which I'm not even sure is necessary, but we don't know if we can remove it. Then we get this bound. So it's actually pretty nice because it's also in terms of the representation theory, this bound. Basically, you have to look at, well, this volume, we could say it's maybe take the length of the largest weight times to the power r. In some sense, it's still polynomial in sort of the weights that appear.
So is this volume assumed to be positive, or somehow what happens if you don't have a maximal?
Yeah, that's a good question. I probably should have said maybe that this is a faithful representation. Yeah. Yeah, maybe the weights normalized. Yeah, anyway, this. Okay. We can also compute the Hilbert series. So idea is sort of similar. We can look again at this expression, determinant of this. Take 1 over that, and then sort of try to average it over the group. But now it's, an integral of such a rational function is maybe not immediately clear what it is. So if we look at that, let's say look at 1 over determinant identity minus t times rho of r, so rho of z, right? So what is this? This is, we have this formula for rho, so this is actually product of 1 minus t times z to the power omega I. And we can expand this as a power series. And then it's a power series not just in t, but the coefficients will be some Laurent polynomials in the z's. And it's a power series in t. And then the invariant ring, the Hilbert series of that, is just a coefficient of z1 to the power 0, z2 to the power 0, zr to the power 0. So you have this series, and now you have to sort of pick the coefficient, sort of the constant coefficient. And in principle, we can do this, and I'll do it in a simple example. So let's take T to be just a one-dimensional torus, rho Z to be, so Z to power -2 Z, Z cubed. So the weights are -2, 1, and 3. Then we can find, so then we just have like one variable here, and we can find the constant coefficient by the residue theorem, right? So then the Hilbert series of OV, so in this case, like the multiplicative group, T is, we take this expression here, which is 1 minus z to the power -2t, 1 minus zt, 1 minus z cubed t. And now, so we take dz over z, multiply it with that, and then we integrate over the unit circle. And then you have to divide by 1 over 2 pi I. Okay, so that's a formula. What is this t? Well, things have to converge so that all power series converge, etc. So let's just say that t in absolute value is smaller than 1, then everything converges absolutely. And so we have this formula. But now we can simplify this, maybe a little, well, not simplify, but I don't like this negative power, so let's multiply with z square. So that I get z square, but then z square also cancels with this, so I get sort of z, and then I can change this to, say, z square minus t. So now we get this integral, but now you know that if you have such an integral, then this is equal to the sum of the residues. So sum of the residues inside this unit disk. So what are the residues? What are the poles? Well, there's a pole at z is square root t, right? So that's maybe z is square root t, and also z is negative square root t. Now these also are also poles, but they lie outside the unit circle. Okay. So now we can use residue theorem, and yeah, I'm just gonna. I'm gonna use this blackboard, so to just keep that formula up there. So this is a sum of residues at z is square root t and z is negative square root t. So then you multiply with z minus square root t, and then you take the limit z goes to square root t, and then some cancellation, and so what you get is something like 1 over 2, 1 minus t to the power 3 over 2, 1 minus t to the power 5 over 2. So that's the residue at the z is square root t, and then the residue at the other one is the same, but we have here plus signs. And then you can further simplify this. In fact, all these non-integral powers actually vanish, and what you get is 1 plus t to the power 4 over 1 minus t cubed, 1 minus t to the power 5. And so that's the Hilbert series. Now, in this, the invariant ring in this case, remember this has weight negative 2, 1, and 3. So you can take x1, x2 square. You can also take x1 cubed and x2 squared. Sorry, x3 squared. And then we can also take x1 square, x2, x3. Now it turns out that if you take this P1 and this P2, then these are primary invariants. And then the secondary invariants, you can take H1 to be 1 and H2 to be this one. And then you see exactly, H2 has degree 4, so that's his t to the power 4. P1 has degree 3, that's his t cubed. And P2 has degree 5, which is this t to the power 5. So it works out nicely. And so that's actually a proof that these three invariants generate. I guess I have to show that these two are algebraic, that they define the null cone, I guess. Anyway. All right, so that's the torus case. Now the next interesting case is, say, a non-abelian group, right? A non-abelian non-finite group. So, well, which is should also be reductive. So, next interesting case is probably the binary forms. And here I'm talking about the group SL2. And so the SL2 acts on the space of binary forms, which is the space of homogeneous polynomials in two variables. So this has been studied a lot in 19th century. So the action is given by the different ways you can let it act. But if you have some polynomial that lies in VD, then this matrix acts by P, say AX plus CY, BX plus DY. That makes this a left action, I think. Now the coordinate ring, so it's a little bit confusing maybe when you see this the first time, because this looks like a space of polynomials, but this is not the coordinate ring, right? This is just the vector space on which the group acts, and then we take the coordinate ring of this. And the coordinate ring of this space is basically, the coordinate functions are the coefficients. So this coordinate ring is just a polynomial ring in these coefficients. So that's a polynomial ring in d+1 variables. And so SL2 also acts on this ring. And so for small d, we can look at the invariant ring. For example, for d is 2, then the invariant ring is generated by the discriminant, which is a1 squared minus 4 a0 a2. Now for 3, degree 3, we also have a discriminant, which is, well, I'm not going to write it down. Also don't know it by heart, but it's some degree 4 polynomial. And for 4, we have two generators, namely G2 and G3, let's say, where these are, of degree 2 and 3 respectively. There's also a discriminant, but the discriminant can be expressed in these two, and the discriminant has degree 6, I think. So when you're working with elliptic curve, you always see these G2, G3 somehow appearing, right? Because if you have an elliptic curve, you can maybe write as y squared is equal to some degree 4 polynomial, for example. Anyway. A lot was already known. Oh, geez. Oh, that's out of reach. So actually, even before Hilbert, there was an algorithm for binary forms by Gordon. In 1867, so algorithm for generators of the coordinate ring, of the invariant ring. And in fact, it's even more general than that. It's also an algorithm for finding so-called covariants, but I'm not going into that. But and so this algorithm doesn't use any Gröbner basis. It's still somehow based on some representation theory. The representation theory of SL2 is fairly simple. For example, the irreducible representations are in fact just the binary forms. These are all irreducible representations of SL2. And you can also know, we also know if you take the tensor product of two irreducible representations, we know how it decomposes because of the Clebsch-Gordon formula, which I may say more about later. There's also a bound by Camille Jordan, I think somewhere, 1876. And they actually gave a bound, d to the power 6. So it's also a polynomial bound in terms of the highest weight, the highest weight of the binary forms is d. So it's kind of a nice bound. So what techniques did they use? So not grammar bases. Although I think some ideas behind like the Grabner base were, I think, also known to some of them. But so one thing you can do is the following. So if we have two forms, let's say P and another form Q, maybe not of the same degree necessarily, then we can do the following. So we can take Px1, y1 times Px2, y2. And basically SL2 still acts on this and this, on both sets of variables. And then we also define this differential operator, omega 1, 2, which is in some sense related to this omega that I described earlier. So this is the determinant of dx1, dy1, dx2, dy2. So then I can apply this to this product polynomial, or I can even apply it k times. And the thing is that this differential operator is SL2 equivariant. And so this gives an equivariant map, and we can set actually the x variables equal to x now, and y variables equal to y. And so now we can get, now we have a form again in two variables, and it's actually a binary form of degree d plus e minus 2 times k, because this omega decreases the degree of this should have been q. Reduce the degree of p by 1 and the degree of q by 1. So this gives us an equivariant map. So it's a bilinear, we get a bilinear map from Vd cross Ve to Vd plus e minus 2k. And it's equivariant with respect to this SL2 action. So in particular, if we take D and E, if we take D as E is equal to K, and let's say it's also even, then we get a bilinear map Vd cross Vd to K. And under these circumstances, but by the way, I should have said probably somewhere that I assume characteristic 0. So this is bilinear, and if D is even, then it's also symmetric. So you can think of it as a quadratic form, which is invariant, right? Because SL2 acts trivially here. So this gives us a degree 2 invariant. Now, using this approach, one can construct lots of invariants. So, for example, we could start with a graph. So, say 1 with 4 vertices. So, let's say a graph where every vertex has degree d. And I'm going to make it an oriented graph, but the orientation is not going to matter that much. So, for example, if I take a d is 3, then I could do this picture. And now we can associate an invariant to that. So I can do sort of the same trick here. I only going to use one form, right? So I have some form px y in Vd, and in this case, d is equal to 3. And I'm going to take px1, start here, px1, y1, px2, y2, px3, y3, px4, y4. Similar like this omega 1, 2, I can define like also omega 2, 4, 2, 3, sorry, 2, 4, I guess, the way I did it. Omega 4, 3, omega 3, 1. And these ones I do square. So you see like how I go from the graph to this expression. Right, so the 2 arrows from 1 to 2, so this omega 1, 2, I do it 2 times, etc. And so this will degree, every number here appears exactly 3 times, so everything will go to something that in the end is constant. And so this will actually give me an SL2 invariant, and the coefficients of P appear 4 times, like there's a product of 4 things here. So it's an invariant of SL2 for binary forms of degree 4 of degree 4, which is, I think, going to be, sorry, no, it was 3, right? Sorry, D was 3. Yeah. So it's going to be this discriminant up to some constant, probably. Now, like I said, the orientation doesn't really matter in this. Now, you may write down graphs, and it turns out that the corresponding invariant is actually trivial, or you can make lots of different graphs, and there will be relations among those invariants. So, for example, some obvious relation is if we switch one of these arrows, that means, for example, omega 1, 2, I change it to omega 2, 1, but then obviously it just changes by a sign. So
D is 3, but it has to be even?
Sorry?
So D is 3, but it also has to be even? What do you mean?
No, that was a previous remark. So the thing is, if so here this invariant corresponds to where you have D arrows, right? But the thing is, if I switch all of them, it's still the same graph. But then, on the other hand, we see that because omega ij is minus omega ji, if I switch one arrow, it changes sign. So if D is odd, that kind of means that it has to be 0. So in other words, so we have this relation. If you switch one arrow, it will change sign, this invariant. And another relation comes from like a Plucker relation. Where did which I always have to wonder about the sign. I think this is correct, but if you want, you can flip some arrows and signs if you want. But so you have relations like that. So if you take 2 arrows and you replace them by other things, you get relations as well. The last thing I could say about, well, there are many things you could say, but the null cone, I think it has already been said in the previous lecture that the null cone, well, let me just say it, yeah. Right? So the null cone for binary forms of degree D are exactly those forms that has a root of multiplicity at least D over 2, more than D over 2. Oh, I didn't say, I guess. Now, you also may wonder about the Hilbert series. It turns out if you have, say, a linearly reductive group, then you can do again this expression and try to integrate it over the whole you can try to integrate over, say, a maximal compact subgroup of G. You take the same expression there and try to integrate over a maximal compact subgroup, but things are always conjugate, or at least there's risk, like in a compact group, everything is conjugate to like a torus. And so in the end, you get some integral that is really an integral over a maximal torus, and then you can again use residue theorems. So in principle, you can also compute Hilbert series of invariant rings for linearly reductive groups. Yeah, I don't have much time left, so I probably won't say anything about non-reductive groups. But maybe I'll just end with a general bound. So we've seen in some cases we have nice degree bounds. For finite groups we have nice bounds. For SL2 we have a nice bound here. In principle, I mean, we can also generalize this. Like if you have more, this is an irreducible representation, but more generally, we may have a reducible representation. For torus, we also have sort of a nice bound. And in principle, we always can get a nice bound when we have a linearly reductive group. So let's say G is reductive. And let's also say the characteristic is now 0. And we have a maximal torus. And V is an n-dimensional representation. And we can again look at the null cone. But we can look at the null cone either for G or for T. So these are the null cone. All right, so this is with respect to G, this is with respect to the action of T. And basically the Hilbert-Mumford criterion says, I mean, that's a way of reformulating it. The null cone for the action of G you get by taking the null cone for the action of T and then moving it around using the group action. Right? If you have a one-parameter subgroup, this one-parameter subgroup will lie in some maximal torus, and you can always conjugate it into any maximal torus you want, and from that kind of follows this. So in some sense, this gives us often like a way of geometrically describe the null cone, right? For example, for the SL2 case, right, you can just look at the action of C star and then look at the null cone for that, and then that's how you get this result about the null cone for SL2. So I'm interested in this beta number, right? This degree bound, but I'm going to introduce another number, gamma of the invariant ring, which is, well, up here it kind of depends on the representation. It's the smallest d, such that if we take the zero set of all invariants of up to degree d, all non-constant invariants up to degree d that are homogeneous, then this is the null cone for G. Right? So if we take all, so if we take d, if d goes to infinity, then this is sort of this mg, and the zero set of that is the null cone. But we know that there's some finite d for which this is also the case by Noetherianity. Okay, I see I'm out of time, so maybe I'll just write down the theorem. That the invariant ring is less or equal than the maximum of 2 and 3/8 as gamma OVG, where S is the dimension of the invariant ring, but I mean it's just bounded by the dimension of the representation. So, oh yeah, there should be a square here. Okay, so this is the bound. Now you wonder, like, okay, now it might be hard to find this bound, and in principle, it's possible to give a bound for this gamma purely in terms of how the group is given by equations and how the representation is given by equations. And just as an example, for SL2, this bound is bounded by 2d cubed. So in that case, you can also bound, which is actually slightly worse than this bound. But then again, it works actually for any linearly reductive group. So that kind of generalizes the bound of Jordan. And I should stop here.
Questions?
So in the case of SL2 acting on the binary forms, is the ring of invariance a polynomial ring, like really generated?
Almost never. But we don't know that many examples, really, because it has only been computed up to, I don't know, degree 10? Okay, yeah, something like that. So it gets hard very quickly. So I think for 2, 3, and 4, it's, for 5, I already don't know. But it's pretty soon it's not a polynomial ring. And typically the number of generators can be huge. But of course we don't really know that much.
So what are we in the theorem? Max of 2? No.
Yeah, I mean, just to get rid of some trivial cases. So this.
Oh, okay.
But in any, almost any example, this will be the bigger of the two. But.
So if I go back to the notes I took on the first of this series, you like we reduce to the cases of looking at invariance in the rings of representations.
Yeah.
But we started with X as an affine variety.
Yeah.
But it seems to me that like all of the calculations are essentially done in the ring, and like it seems that this should be fine to do on a projective variety as well, because like you're just taking proj instead of spec, right? So does all of this, or like at least the bulk of this, like work sort of locally? If you want, like, is it just a matter of like doing the same thing for a projective, but then
yeah, I don't know if you mean by locally looking at sort of a cover of stable affine things, and you want to glue it together. I'm not really sure what happens when you glue it together, but because for one thing, for example, right, you could there are examples. Yeah, I mean, like for. Yeah, I think if you glue things together, like you could glue some affine varieties together to get a quasi-affine variety for which the coordinate ring is not finely generated, things like that. So I don't know. My feeling is that in that way, yeah, I'm not sure. But if you start with some projective coordinate ring and you have some group action and then take invariants and so on, yeah, then basically you're doing things over affine varieties, and so then everything is fine.
I see. Okay. Thank you.
we have another question? Are there people online who have questions?
Yes.
Yeah.
Go ahead.
Oh, go ahead.
Online questions?
Yes, I'm Abdul Halim. I have a question.
Go ahead.
Yes. My question is that in this talk you have used the Molian formula
Yeah.
over a finite group.
Yeah.
Is it possible to do on non-finite group?
Yeah, so basically what I did here for the tori or for C star is basically a Molian's formula for infinite groups. And in principle, it generalizes to linearly reductive groups.
Okay, thank you so much.
But it gets more complicated because you have to do residue theorems and things like that.
Yeah, finding this one.
But in principle, you can it's still a lot easier than computing the invariant ring, the generators. So, yeah. So, for example, for binary forms, you can easily compute the Hilbert series for the degree 30, 40, whatever. But we cannot compute
Yes,
the
it is easy
generators.
for it. Alternative group A3, S3 is it's easy for it.
Yeah.
Okay, thank you so much. Very nice talk.
Thank you.
More questions in this audience in Cambridge? All right, so we'll first thank the speaker and then